welcome to lecture 4 on trigonometric functions. In lecture 3 we discussed and derived expressions for sin x plus y, sin x minus y, sin 2x, sin 3x, cos 2x, cos 3x, and we also formally defined the tangent function. In today's lecture we will derive more expressions for the tangent of the sum of two angles and the difference of two angles, the tangent of twice of an angle and thrice of an angle, and we will introduce some more trigonometric functions like cosecant of x and secant of x, followed by some problems. So, let us try to derive an expression for tan of x plus y in terms of tan x and tan y. Of course, as we know that tan of x is not defined when x is an odd multiple of pi by 2. So, the following expression is going to be valid only when x plus y is not an odd multiple of pi by 2. Now, since tan of x is sin x by cos x, so tan of x plus y is equal to sin of x plus y upon cos of x plus y. In the previous lectures, we derived expressions for sin of x plus y and cos of x plus y. So, using that we can write sin of x plus y as sin x cos y plus cos x sin y upon cos x cos y minus sin x sin y. Now, dividing both the numerator and denominator by cos x cos y, we get. So, when we divide this term by cos x cos y, we get tan x because the cos y gets cancelled with cos y, and so this is what we get, sin x cos y divided by cos x cos y plus cos x sin y divided by cos x cos y upon and this is, so this term is tan x, this term is tan y, this is 1, and this is tan x times tan y. So, finally, we get tan of x plus y equals tan of x plus tan of y over 1 minus tan of x tan of y. This expression is valid only when all of x, y and x plus y, all these three are they are not odd multiples of pi by 2, because tan of x is not defined when x is a odd multiple of pi by 2, it becomes unbounded. So, this particular expression gives you a relation between the tangent of sum of two angles expressed as in terms of the separate tangents of the two angles. From here, it is very easy to now derive the expression for tan of x minus y, because that can be written as tan of x plus minus y, and then we use this equation again. So, essentially in this equation we replace y with minus y. So, we get tan x plus tan of minus y upon 1 minus tan of x tan of minus y. We have seen from the previous lecture that tan of x is an odd function of x. So, tan of minus y is minus of tan y. Using that, we get this to be equal to tan x minus tan y upon 1 plus tan x tan y. Let us now compute the expression for tan 2x. From the previous slide, we saw that tan of x plus y is equal to tan x plus tan y upon 1 minus tan x tan y. So, using this expression and substituting y with x, what we get is tan of x plus x, which is tan of 2x, equals tan x plus tan x. So, that is 2 tan x upon 1 minus tan square x. But again, this is well defined only when 2x is not an odd multiple of pi by 2 and also x, because if x is an odd multiple of pi by 2, then this tan x here and this tan x here is also not defined. In a similar manner, we can derive the expression for tan of 3x. Again, using the expression for tan of x plus y, we get tan, we have seen from the earlier slide that tan of x plus y is tan x plus tan y upon 1 minus tan x tan y. So, substituting y to be equal to 2x, we get tan of x plus 2x equals tan x plus tan 2x upon 1 minus tan x into tan 2x. And then we use the expression of tan 2x from the previous slide, which I just reproduce it again for your convenience. So, tan 2x is 2 tan x upon 1 minus tan square x. So, using that expression here, what we get is tan x plus 2 tan x upon 1 minus tan square x upon 1 minus tan x times 2 tan x by 1 minus tan square x, and then multiplying both the numerator and denominator with 1 minus tan square x, we will get tan 3x to be equal to tan x times 1 minus tan square x plus 2 tan x upon, so that is the numerator, 1 minus tan square x minus 2 tan square x, which is equal to, and then opening up this these braces here, we finally get tan 3x to be equal to 3 tan x minus tan cube x upon 1 minus 3 tan square x. Again this is well defined only when 3x is not an odd multiple of pi over 2. We had introduced the cotangent function cot x, and we had defined that cot x to be equal to 1 upon tan x. So, in this slide we will be trying to derive an expression of cot of x plus y in terms of cot x and cot y. So, from here it follows that cotangent of x plus y is 1 upon tan of x plus y, and we know the expression for tan x plus y, which is tan x plus y is tan x plus tan y upon 1 minus tan x tan y. Using this expression here in the first equation here, we get cot x plus y equal to 1 minus tan x tan y upon tan x plus tan y. Now, dividing both the numerator and denominator with tan x tan y, we get 1 upon tan x tan y, so which is this term here, minus tan x tan y divided by tan x tan y will give you a 1, divided by tan x upon tan x tan y plus tan y upon tan x tan y. So, here this will get cancelled and here tan y is going to get cancelled. This particular term here is nothing but 1 upon tan x times 1 upon tan y. 1 upon tan x is cot x, 1 upon tan y is cot y. So, this term here is cot x times cot y, and 1 upon tan y here is cot y, 1 upon tan x is cot x. So, finally, we end up with the expression cot of x plus y equals cot x cot y minus 1 upon cot x plus cot y. Now, since cotangent of x is 1 upon tan x, which is actually cosine of x upon sine of x, cotangent of x becomes infinity plus minus infinity when sine of x goes to 0, which happens when x is a multiple of pi. So, this expression for cotangent of x plus y is well defined only when x plus y is not a multiple of pi. And of course, from this expression of cotangent of x plus y, we can get the expression for cotangent of x minus y. We just need to replace y with minus y in this equation here. Now, since cotangent of x is 1 upon tan x and tan x is an odd function, so it follows that cotangent of x will also be an odd function. And therefore, cot of x minus y, by replacing y here with minus y, we get cot of x into cot of minus y minus 1 upon cot x plus cotangent of minus y. So, cotangent of minus y, because cotangent of x is an odd function, cotangent of minus y will be minus of cot of y. So, this will become 1 plus cot x cot y over cot y minus cot x. And this expression is again well defined only when x minus y is not a multiple of pi. So, just like we derived the expressions for tan of 2x and tan of 3x, we can derive the expressions for cot of 2x in terms of cot of x. We saw that cot of x plus y is cot of x times cot of y minus 1 over cot of x plus cot of y, and therefore, substituting this y to be equal to x. So, with y equal to x, what we end up getting is that cot of 2x is equal to cot x into cot x, that is cot square x minus 1 divided by 2 times cot x. So, we got an expression for cot of 2x in terms of cot of x. And similarly, we can also derive a function of for cot of 3x in terms of cot of x. We substitute y with 2x in this equation, we get cot of x plus 2x, which is 3x, equals cot of x into cot of 2x minus 1 upon cot of x plus cot of 2x, and then we use the expression for cot of 2x from the previous slide. So, we get cot of x into cot of 2x was cot square x minus 1 upon 2 cot x. So, multiplying the numerator and denominator with 2 cot x, we finally get and this again is defined only when 3x is not a multiple of pi. So, in one of the previous slides, we had defined the cotangent function to be 1 upon the tan function. So, just like that, we have to we define another function called the cosecant function. So, the name of the function is cosecant, but we usually call it cosec in short, and it is defined as cosec of x equals 1 upon sin x. So, from this definition, it obviously follows that the domain of the cosecant function will be the same as the domain of the sine function, which is the set of all real numbers. Further, we know that for any x real, mod of sin x is less than equal to 1, but cosecant x is 1 upon sin x, and therefore, from this relation and this fact, it follows that mod of cosecant x for any x real is always greater than equal to 1, from which we can say that the range of the cosecant function is therefore the union of the two intervals. The first interval is from minus infinity to minus 1 union with, so the value of minus 1 will be there in the set, union with the other interval is from 1 to infinity. So, this is the range set of the cosecant function. Just like the way we define the cosecant function, another very popular trigonometric function is the secant function. The name is secant. In short, we write it as sec. Sec of x is defined as 1 upon cos x, and therefore, the domain of the secant function will be the same as the domain of the cos function, which is the set of all real numbers. And again, just like as in the case of the cosecant function, since for any x real, mod of cos x is less than equal to 1. So, using this fact and this definition, it follows that for any x real, mod of secant x has to be greater than equal to 1, and therefore, we can write that the range of the secant function is again the same as the range of the cosecant function, which is the union of the interval minus infinity to minus 1 union 1 to infinity. Now that we have learnt a lot of identities and relations between different trigonometric functions and also expressions for the sum and differences, the tangents and the sine and cosine of the sum and differences of angles, let us try to solve some problems. So, in this problem it is asked to show that the expression on this left hand side is equal to cot of 2x. So, the main idea of solving problems is to find patterns and to try to apply the expressions and identities that we have learnt to patterns that you find out in the expressions in the question. For example, here we see that on the left hand side we have sum of two cosines, and if you remember, we had this identity that cos of A plus cos of B equals 2 times cos of A plus B upon 2 into cos of A minus B upon 2. So, this was taught in one of the previous lectures, and so this is the slide from the previous lecture where we had shown this identity of cos A plus cos B to be equal to 2 times cos A plus B by 2 times cos of A minus B over 2. And since we are getting this pattern here cos A, so this is A is 7x, B is 3x. So, by putting A equal to 7x and B equal to 3x, what we get is cos of 7x plus cos of 3x is 2 times. So, A plus B is 10 of 10x, and that divided by 2 will give you cos of 5x, and A minus B is 4x, so upon 2 will be 2x. So, cos of 2x. And then in the denominator we see a pattern of the form sin A minus sin B, and this was also discussed in one of the previous slides in lecture 3, which I reproduce it in front of you now. So, sin A minus sin B, this expression was derived. So, we will try to use it here. So, let me rewrite it for you. Sin A minus sin B equals 2 times cos of a plus b over 2 into sine of a minus b over 2. So, again putting a equal to 7x and b equal to 3x, we get sine of 7x minus sine of 3x equals 2 times cos of a plus b over 2 will be 5x and a minus b over 2 will be 2x. So, finally we get these expressions for the numerator and the, so this is for the numerator and this is for the denominator, and then when we divide these two, it is equivalent to dividing this by this. So, what we get is that the left hand side here will be equal to, the numerator is equal to 2 cos 5x into cos 2x, and this denominator is equal to this expression here 2 cos 5x times sine of 2x. So, 2 and 2 gets cancelled, cos 5x and cos 5x gets cancelled. What remains is cos 2x upon sine 2x, which is equal to cot of 2x, which is the right hand side here, and that completes the proof of the fact that this is equal to this. So, what we learnt here was to find out patterns in the question or in the expressions that are there, and try to see if we can apply whatever expressions we have previously learnt to the question here. For example, in this case we identified the patterns cos A plus cos B and sin A minus sin B, and we expressed them as product of cos and sin, which led to the cancellation and then final answer. Another similar question here, we have the sum of 3 cosines. So, either we can start with adding this and this first, and then we add this to the sum of these two, or we can add cos 3x and cos 5x first and then later on add cos 4x. So, which way do we go? Do we add cos 3x with cos 4x using the cos A plus cos B formula and then add cos 5x? The problem is that if we add cos 3x and cos 4x first, if you remember the formula for cos A plus cos B, it is 2 cos A plus B by 2 into cos. The terms that we will get is cos 7x by 2. So, if we take A to be 3x and B to be 4x, so if we are adding this and this, we get 2 times cos 7x by 2 and times cos x by 2. The problem is that then these two terms have nothing in common with cos 5x. So, it will be very difficult to factor out something common, because ultimately if you see what we need here on the right hand side is 4x. So, therefore, trying to add this and this first is not the right strategy, it will lead to waste of time in the exam. So, the other option could be to add 3x and 5x, and that is better, because when you add 3x, so when you add cos of 3x plus cos of 5x, what you get is 2 times cos of 4x times cos of x. So, this is cos 3x plus cos 5x. Now, you also need to add cos 4x now, but the good thing now is that this already has this cos 4x factor. So, it becomes easy to further combine this term and this cos 4x, and the other thing is that the right hand side also has 4x. So, that is why we should take this route. Instead of adding 3x and 4x first, we should add 3x and 5x first. So, then the numerator can be written as, so the numerator of the left hand side can be written as 2 cos 4x times cos x, which is the sum of cos 3x and cos 5x, and then plus cos 4x. So, cos 4x can be factored out and it can be written as cos 4x into 1 plus 2 cos x. So, for the same reason in the denominator we will try to add sin 3x with sin 5x first. So, if you remember the formula for sin A plus sin B, and this was derived in the previous lecture to be equal to 2 sin A plus B over 2 times cos of A minus B over 2. So, therefore, sin of 3x plus sin of 5x equals 2 times sin of 4x, because a is 3x and so a plus b is 8x upon 2, it becomes 4x, into cos of a minus b by 2. So, a minus b is minus 2x. So, cos of minus 2x upon 2 is cos of minus x, but cos of minus x is the same as cos of x. So, this is what we get, and then the final expression for the denominator on the left hand side will be, we just add this expression to sin 4x. So, what we get is sin 4x again is common. So, we can write it as sin 4x times 1 plus 2 cos x. So, this is the denominator. So, this is the numerator and this is the denominator, and then finally, when we divide the numerator by the denominator, what we see is that this term 1 plus 2 cos x is there in both the numerator and the denominator. So, when we divide, it gets cancelled, and then we get cos 4x divided by sin 4x, which is equal to the right hand side, which is cot 4x. So, through this example we saw that it is very important that we decide which factors should be added first, otherwise it might result in loss of time. Another interesting problem is the following. So, it is asking us to compute the value of sine of 18 degrees. Now, what we realize here is that since sine of x is equal to cos of pi by 2 minus x, this is another identity that we had discussed in the previous lecture. We see that sine of 36 degrees is equal to cosine of 54 degrees. The reason why we have chosen 36 and 54 is because, first of all, they add up to 90 degrees. The other reason being that they are both multiples of 18 degrees. So, the idea is to use the formula for sine 2 theta and cos 3 theta with theta equal to 18 degrees, because with theta equal to 18 degrees, 2 theta is 36 degrees and 3 theta is 54 degrees. Now, we know that sine 2 theta is 2 sin theta cos theta, and we also know that cos of 3 theta is 4 cos cube theta minus 3 cos theta. Both these expressions were derived in the previous lecture. So, from here what we get is that with theta equal to 18, since this and this is equal, we can write that 2 sin theta cos theta minus 4 cos cube theta minus 3 cos theta equals 0, because this is sin 2 theta and this is cos 3 theta, and for theta equal to 18 degrees they are equal. Now, we see that cos theta is a common factor in all these terms. So, we can write this as cos theta into 2 sin theta minus 4 cos square theta plus 3 equals 0. But so the possible solution here is that either this term is 0 or this term is 0. But for theta equal to 18 degrees, we know that cos of 18 degrees is not equal to 0. Therefore, the only way this equation can be satisfied is if this term is equal to 0. That is, for theta equal to 18 degrees, this equation is satisfied. 4 cos square theta minus 2 sin theta minus 3 equals 0. But we know that cos square theta is equal to 1 minus sin square theta. So, using that we get 4 minus 4 sin square theta minus 2 sin theta minus 3 equals 0, and well, taking it to the other side, that can be written as 4 sin square theta plus 2 sin theta minus 1 equals 0. So, theta equal to 18 degrees satisfies this equation. Now, this is basically the left hand side here is a quadratic polynomial in sin theta. So, let us say that z we define it to be sin theta. So, what we get is 4 z square plus 2 z minus 1 equals 0. So, there are two possible solutions to this quadratic equation, and the solutions are z equals minus 2 plus minus of 20 by 8. Since sine of 18 degrees is positive, the only possible root that makes sense is with the plus sign here. So, we finally get that sine of 18 degrees is equal to minus 2 plus root over 20 upon 8, which can also be written as square root of 5 minus 1 upon 4. Some more problems moving ahead. So, in this problem we are asked to again prove that this expression on the left hand side and this expression on the right hand side are both equal. So, if we see the expression on the right hand side, we know that cosecant of x is 1 upon sin x and cotangent of x is 1 upon tan x, but we can also write it as cosine of x upon sin x. So, this becomes equal to 1 minus cosine of x by sine of x. So, what we see now is that this 1 minus cosine x comes here as well as here. So, if you want this numerator to be equal to, but the problem is that here 1 minus cos x is inside the square root. So, for 1 minus cos x to be outside the square root, one way to do that is that we multiply the left hand side, both the numerator and the denominator, with square root of 1 minus cos x. So, we multiply both the numerator and the denominator of the left hand side with square root of 1 minus cosine x times So, the numerator now becomes 1 minus cos x as what we wanted, and the denominator becomes root of 1 upon cos square x, but we know that 1 minus cos square x is sin square x, and then the root of sin square x will be sin x. So, this is equal to, which is nothing but the right hand side here. So, that finishes the proof for this question. Some more tricky problems. So, in this question we are asked to find the value of cos of 40 degrees minus cosine of 20 degrees plus cosine of 80 degrees. So, at first this might appear to be a very tough problem, because all these angles are angles for which the sine and cosine is not known to us. We typically usually remember sine and cosine of 45 degrees or 30 degrees or 60 degrees, or maybe we can calculate it for 15 and 75 degrees. So, this might appear a little daunting, but then the trick to be seen here is that again we see that we are adding and subtracting cosines. So, immediately we should try to recollect the cos A plus cos B formula, which is cos A plus cos B equals 2 cos plus B upon 2 into cos minus B upon 2. So, this gives some hope, because if we choose this A and B correctly from these three terms, then maybe one of these cos angles, either A plus B by 2 or A minus B by 2, could be an angle for which we know the value of cosine, and that might help us to solve the problem. Now, looking at these three angles, we see that if we take A to be 40 degrees and B to be 80 degrees, then we see that 40 plus 80 divided by 2 is 120 divided by 2, which is 60 degrees, and it is, we know that cosine of 60 degree is half. So, let us try this route, this path. So, cos of 40 degree plus cos of 80 is, using this formula, 2 times cos of 60 degrees times cos of 80 minus 40. So, that is minus that is 40 upon 2. So, that will be 20 degrees. So, this becomes equal to, now cos 60 degrees, we know that cos of 60 degree is equal to half. So, putting it here, we get this to be equal to cos of 20 degrees, and then the final expression is obviously 0, because this the sum of cos 40 and cos 80 is cos 20, and we are subtracting cos 20 here. So, the final answer is 0. This is a problem from one of the JEE exams. So, again, to start with, this problem looks very terrifying, because you go all the way to 8 theta, starting from theta. But again, what we have to always do is to see patterns in the expression. So, the pattern here is that from the first expression to the second, from the first term to the second term, the angle inside the tangent is doubling, and again from here to here it is doubling, and then again here to here. So, probably they are, it seems like the formula of tan of 2x might be handy. So, if you remember, tan of 2x was equal to 2 tan x divided by 1 minus tan square x. Now, let us start from let us start with the left hand side. The last term in the left hand side is 8 times cotangent of 8 theta, which can be actually written as, so cotangent of 8 theta is 1 upon tan 8 theta. So, taking x to be equal to 4 theta, we have tan of 8 theta equals 2 tan of 4 theta upon 1 minus tan square 4 theta. So, to get this term we need to invert this expression. So, what we get is 8 cot 8 theta plus 4, and we realize that this cot 8 theta expression will have tan of 4 theta, and the next expression, the next term is tan of 4 theta. So, we will try to combine it with it. So, 8 cot 8 theta plus 4 tan 4 theta will be equal to 8 into 1 minus tan square 4 theta by 2 tan 4 theta plus 4 times tangent of 4 theta. So, this becomes 4. So, that is equal to 4 times, because we have 4 here and here also, and we simplify it. So, it becomes, so this becomes 1 upon tan 4 theta, because tan 4 theta times tan 4 theta is tan square 4 theta, that gets cancelled with this minus tan square 4 theta here. So, the left hand side now reduces to tan of theta plus 2 times tan 2 theta, and then plus 4 by tan, and then we repeat the same process. We write tan 4 theta to be equal to 2 times, because now the next term after before this term is tan 2 theta. So, we would like to express this tan 4 theta in terms of tan 2 theta. So, that probably will be, when we combine this and this term, we might be able to cancel some terms there. So, that is the idea. So, then when we look at this sum, what we get is 4 upon tan 4 theta plus 2 times tan 2 theta is equal to 4 into 1 minus tan square 2 theta upon 2 tan 2 theta plus 2 tan 2 theta. This 2. So, we get here 2 upon. So, if you simplify this, you will get 2 upon tan 2 theta, and then finally, the left hand side. So, this is the left hand side. So, finally, the left hand side becomes tan theta plus 2 upon tan 2 theta, and now again using the, we need to express tan 2 theta in terms of tan theta. So, that there could be some cancellation of some terms here. We know that tan of 2 theta is 2 tan theta upon 1 minus tan square theta. So, using this expression here, what we get is this to be equal to tan theta plus 2 into 1 minus tan square theta by 2 tan theta. So, this gets cancelled, and so this tan theta will get cancelled with this minus tan square theta by tan theta. So, ultimately what will remain is 1 by tan theta, which is actually cot theta. So, that is what was the right hand side. So, that finishes the proof of this seemingly very difficult problem. So, let us discuss another problem here. So, again we have to show that this left hand side is equal to this right hand side, and even here we see a pattern that there is an angle A and then 2A and then 4A and then 8A. So, what we see is we see a sin 8A and a cos 4A, and that should immediately ring an alarm bell in your minds that we know that sine of 2 theta is 2 sine theta cos theta. So, if we put theta equal to 4a, what we will get here is sine of 8a is 2 sine 4a cos 4a. So, we get a cos 4a here, and that should hopefully cancel this cos 4a. So, if we look at this right hand side, what we will get is sine 8a upon 8 sine a will be simply 2 sine 4a into cos 4a upon 8 sine a. So, at least now we have got one term which is there on the LHS. So, now we just need to show that this is exactly equal to, so we need to show that this is equal to cos a into cos 2a, and that can be done similarly because we know that sin 4a will have this cos 2a term again using this formula, but with theta equal to 2a, what we get is sin 4a equals 2 sin 2a into cos 2a. So, therefore, so we have to show that 2 sin 4a upon 8 sin a equals, so this is what we have to show, and just now we derived this expression that sin 4a equals, so this is what we have to show actually. We derived this expression, we wrote that sin 4a is 2 times sin 2a times cos 2a. So, now replacing this sin 4a with this over here, what we end up getting is sin 2a into cos 2a upon 2 sin a. So, if so this thing is equal to this, and you can see that now we also get this cos 2a term here. And now it is very easy because we know that sin 2a. So, if we now just look at this term, that term is nothing but 2 sin a cos a is sin 2a upon 2 sin a. So, this gets cancelled, and then this becomes equal to cos a and cos 2a. So, this becomes equal to cos a times cos 2a. So, what should be realized by these examples is that we should always try to see for patterns and try to make the right judgment in terms of the route to be followed for the proof, because most of these competitive exams are time bound. And in the next lecture, we will continue to solve some more problems which will basically make you comfortable with solving these type of problems. Thank you.